So I'm Jonathan. I work at CoreOS. Been there for a couple of years, working on a bunch of different things, but most recently focused on some of the Rocket, some of the container stuff we've been doing, which includes primarily Rocket and how we integrate with Kubernetes. So I'm going to I like to start these by sort of setting a bit of context and like looking at our motivation for why we're working on this stuff at CoreOS, because it really guides like all of our design decisions and where we're kind of going with this. I'm going to go through it really quickly since everyone here is probably pretty familiar with Kubernetes and containers and sort of why we're doing these things. But just kind of break it down, like fundamentally, like why do we care about container runtimes and orchestration at all? Because really that's what Rocket and Kubernetes are. If we step aside from the specific technologies, just kind of like the general problems that we're trying to solve. So at CoreOS, this is all really about security. Our mission is like securing the internet, pushing application server security forward. And the kind of key insight that like drives a lot of the technology at CoreOS is that we want to make updates as seamless as possible. So that started with the operating system itself, CoreOS Linux, which is sort of our flagship product. That's a minimal operating system that automatically updates. And the key way that we sort of facilitate these automatic updates is by using containers. So the basic idea is that if you're updating the operating system all the time, you need to be able to abstract the applications that are running on the operating system away, so that when we update the operating system without a user, without a user triggering it, we don't affect the application that's running. And so containers and orchestration are two sort of high-level abstractions to facilitate this. So first, containers, decouple the actual software that's running in the operating system that we're going to be changing when we're providing those automatic updates from the user code, so that user's application can keep running and we can change libraries underneath them. And then orchestration sort of decouples the life cycle of the application from the operating system uptime. Again, I'll just kind of skim through this very briefly, but what it means to decouple the user space, the application code from the operating system. In the classic world, the operating system will be responsible for providing more of these sort of libraries and virtual machines and things that your application depends on. But in a sort of modern containerized ecosystem, all of that responsibility is shifted into the application container. So now the distribution on the left, which is in this case now CoreOS, is responsible for a much smaller set of software. So we can update that software very, very quickly without affecting, without breaking this contract that we're providing to the application developers on the right. And then now application developers are responsible for packaging all of the necessary dependencies alongside their code. We don't have to worry about it. I would never recommend running multiple SSL versions because probably one of them is horribly broken. So again, that's kind of what CoreOS is. That's how that's kind of where the company started and where our sort of project started. And then once we kind of had the operating system, then we started to look at different parts of the stack and where we thought things were lacking. So the next thing to kind of think about is once you have this operating system that's automatically updating, it's great. You're not affecting user code, but you're still affecting uptime, because fundamentally for us, when we apply an update, it involves a reboot. And there's a couple of technical reasons for that. Arguably it's also sort of good hygiene to get to a completely clean known state. We have experimented with using things like kexec to sort of update the kernel in place, but fundamentally we still think reboot is a good way to sort of apply an update to the operating system image. So obviously there's a problem though if you're running your app in your cluster, and so in this case we're running a few apps spread across the cluster of 3 machines. When your first server tries to update the operating system, needs to go down for a reboot, suddenly you lose availability of all the applications that were running on that server. Of course, this is sort of an old world when you didn't have some kind of orchestration system. So while that server's rebooting, you lose availability of the apps running on that server. Suddenly, if we introduce what I'm calling now sort of a magical orchestrator, now at the time when the first server applies the applies the update and sort of is aware that it needs to reboot, the orchestrator can now sort of migrate those apps to different servers, so that now when the server's rebooting, you still have that continuity of the application uptime. Then once the server's actually been updated, it's back up and running successfully, then the orchestrator can maybe migrate apps back just to ensure that they're sort of the load is shared across the different servers. And I've said magical orchestrator. Well, for us, that's Kubernetes. So Kubernetes is responsible for distributing applications in the cluster and migrating them when servers become unavailable. So again, that's kind of was like the 5-minute, very quick summary of why we're working on all this stuff, why we're interested in container runtimes and orchestration. It's so ultimately so that we can provide seamless updates to the operating system and push forward the security of application servers. So that's why we're interested in those things. But why Rocket? Again, I'm going to talk a little bit about the motivation, and then I'll kind of jump forward to today. So we go back to sort of the end of 2014, which is when the Rocket project started. This was sort of before the classic container wars came out. I hate this term. We're not interested in any wars or anything. We just want good solid technology. So I'd appreciate if you'd help me trying to kill this meme. But basically, at the time there was a very, very popular container tool, Docker, out there, and which we ship in CoreOS by default. We'll continue to support it, but it was a few sort of issues that we had with Docker that we felt were less than ideal, and sometimes some of these issues that we tried to work on and sort of get upstream, and unfortunately we didn't have much success in necessarily integrating them. Also, just sort of some missing best practices we thought in the ecosystem. So, for example, things like by default never requiring image signatures or anything like that. So just sort of running arbitrary bundles from the internet. Some of the build approaches around building container images we thought were less than ideal. For example, like the classic pattern of building from a kind of standard operating system image from like an Ubuntu image. We think that can pull a lot of sort of unnecessarily dependencies and things into your container. And then there were quite a few sort of technical issues that we had integrating Docker with CoreOS, and particularly as we started to explore sort of container orchestration. So the classic example is that it's very difficult to integrate Docker with systemd. CoreOS, for those not familiar with systemd, it's sort of an init system that's going to become the default init system on most Linux distributions. We've been using it in CoreOS for a very long time. Systemd is quite opinionated. We think it makes a lot of the right choices, and that ultimately it's going to be the best system to kind of bet on in the long term. Unfortunately, systemd and Dockerd have a lot of kind of overlap in areas that they're trying to control, like in the operating system. So things like C groups, for the classic example, and it can be, there's a lot of sort of impedance when you're trying to integrate these two systems. So this sort of spurred us to create Rocket with kind of the three sort of key goals. The first was really just to kind of create an alternative to Docker and really drive like innovation in the ecosystem. And then the second was kind of to try and drive this conversation around security and composability. So we CoreOS, we really try to emphasize like the Unix philosophy of build tools that have a small scope and integrate well with other tools. And we didn't think that was always reflected in sort of the Docker ecosystem. So we want to build tools like Rocket or like etcd that have very, very well-defined scope and don't try to implement all these different areas of the stack, and then we can just kind of plug them together and people can swap them out for different components. And then we also wanted to drive this conversation around standards because we felt that was really lacking with containers. So for example, what is a container image format? There was like a de facto image format. There was nothing really written down that people could go out and build their own systems against, build their own tools against. So that's what Rocket is. We call it kind of a modern secure container runtime. And the reason we call it modern is because we try to take advantage of a lot of the newest technologies in Linux. So as new file systems or security technologies emerge, we try to take advantage of them very quickly in Rocket. It's simple and composable, so it has a small scope compared to some sort of container systems. And we design it to really try to focus on integrating with other systems rather than it doing everything internally. And we try to make it's an implementation of an open standard. So just to touch on that standard very quickly, the standard that Rocket sort of first implemented is AppC, which is the thing we announced kind of in parallel with it, and that's trying to solve that thing that I talked about defining, like, for example, what an image format is. AppC, not sure what happened there. AppC is it's a collection of projects. It's all on GitHub. The crux of it is like the specification, which again is what defines what the image format is, for example. And then there's some other tooling to work with it, to convert between Docker images, AppC images, to build images, some networking stuff, which I'll talk about in a little bit. But today, for our purposes, I'm mostly really interested in talking about pods, actually. So pods, is the kind of the key execution primitive in AppC. So this is sort of like when we're trying to define what does it mean to actually run a container or run applications in a container. And pods is this concept popularized by Kubernetes, which is that the fundamental execution unit is a grouping of apps. We think that's a really, really powerful primitive, and So that's the only execution primitive in appc. And essentially the definition is the same between what appc defines as a pod and what Kubernetes sort of implements. appc just tries to be a little bit more explicit about things like the life cycle of a pod, what exactly it consists of and stuff like that. appc is also a little more agnostic in that it's sort of more cross-platform than something like Kubernetes. But fundamentally, appc pods and Kubernetes pods are the same thing. And the reason why I'm talking about this is because this has implications for when we talk about integrating Rocket with Kubernetes. So again, Rocket's modern secure container runtime. It's designed to be very composable and sort of integrate with other things. And it implements appc, which was our effort to sort of create a standard. Fast forward a year and a bit, Docker and Rocket are now both considered production ready. Put that in quotes because when is something really production ready? But what I mean here is people are using it in production. We both saying we're supporting it in production. We think that they've reached a level of maturity where you can really make sense to go out and build against them. And Kubernetes as well, obviously. And then sort of on the standards front, in terms of defining what application containers are and what container runtimes should do, there's been a couple of developments. So as I said, appc was launched in December 2014. Back in around June 2015, there was a new project called the Open Container Initiative, started by a group of pretty wide body of different companies, including CoreOS and Docker and Google. And the purported goals of that was to sort of create a standard around application container sort of images and runtime formats and things like that. More recently, there's been the creation of the CNCF, the Cloud Native Computing Foundation, which is probably a little more sort of oriented around projects rather than standards per se, but still potentially, as part of its goal is to kind of try and harmonize these different standards around running applications in containers. I'm not going to talk about this stuff too much today, but I'm very happy to talk more if anyone wants to come and find me afterwards about standards and where this stuff's going to end up. I'll just talk a little bit later on about how that's relevant to actually what we're doing. But since I want to talk about Rocket, let's dive in pretty quickly through the sort of Rocket architecture, and then we'll see how it integrates with Kubernetes. So as I said, Rocket's fundamentally a simple CLI tool that you can just run on the command line. There's no central daemon that has any sort of key responsibilities. There's no API that's sort of necessary, but we do provide an optional API. And the Rocket architecture means that any applications you run directly underneath a Rocket command that you run, which means that whether you're running it from a command line or whether it's started by your init system like systemd or started by the kubelet in the case of Kubernetes, the applications run directly underneath the process. The really nice thing about that is that any sort of constraints and parameters you apply to the to the Rocket process will apply to the applications, which is pretty different to the Docker model where applications are sort of submitted to a different daemon to run instead. So internally, Rocket has this staged architecture with sort of 3 key stages, and the reason for that is so that we can take advantage of different technologies internally. So, for example, at the stage 1 level, but the external interface that we provide to users, which is at stage 0, is consistent. So we can take advantage of new technologies without end users noticing. They get exactly the same experience when they're running applications. What that actually looks like is that, so actually I said here that Rocket was running applications, but really what it's running is pods, and then a pod internally can have 1 or more applications. So kind of showing what the stages actually look like in a little more detail. The Rocket command line tool, that's the stage 0, and that defines the interface that users interact with. Then internally, Rocket sort of encapsulates the pod in something we call the stage 1, and that's responsible for setting up things like the classic constraints that we think of with containers, so maybe namespaces and C groups. And then within that stage 1 is where the different applications actually run. Stage 0 does everything you'd pretty much expect from a container system in terms of you can run containers, you can look at running containers, you can download images and things like that. And mostly it's responsible really for just like the glue, the stuff that like reaching out across the internet, finding images, downloading them, checking signatures, stuff that we think is good to do in a safer, higher level language like Go. And again, that defines the interface that users interact with. And then internally, stage 1, which does all sort of the nuts and bolts of setting up the container, that's where it's swappable, and that's where most of this is actually kind of implemented in C. And by default, we use systemd nspawn-based implementation, which actually sort of invokes systemd nspawn. And that way we get to take advantage of all the work that is happening in nspawn and just sort of leverage that directly in Rocket, and we don't need to re-implement all that code. So the default implementation is like a classic Linux container using C groups and namespaces to set up isolation. And then the other implementation that we maintain upstream is a KVM-based one, which is pretty cool because that uses a really lightweight LKVM process, spins it up, and then it starts up the pod inside that thing. So then you get the full like virtualization, hardware virtualization containment. But again, since this is staged from stage 0 in terms of interacting with Rocket, everything looks exactly the same. So you can swap out and get the advantages if you have hardware virtualization support of getting VM containment, but the interface to Rocket looks exactly the same, and the experience is exactly the same. And then finally, we have a couple of other kind of proposed implementations around something like Xhive, which would allow Rocket to do virtualization potentially to run containers potentially on OS X, or something called Unc, which is a way to run unprivileged containers using I think pure Go. Finally, inside the pod itself, stage 2 is where the applications run. That just every application, again, this is just like the Kubernetes definition. Every application has its own file system, but they share things like they share network namespacing. They can see each other processes. They share a PID namespace, and they share access to certain volumes, things like that. A couple of the features that we've added recently to Rocket. One of them is called TPM measurement. So the TPM, for those of you who aren't familiar, it's a hardware chip on some modern motherboards that allows you to. It sort of contains some cryptographic keys and can do some cryptographic operations, and allows you to measure the state of like code that executes on the system. So primarily, historically, just used to like check the boot process. So for example, verify what bootloader is and OS actually running. That used to only work on proprietary operating systems, but at CoreOS, Matthew Garrett adds support to Grub, so now we use that within CoreOS. And then he's also added support to Rocket itself. So when you're, the idea is that from the point in time at which you boot the system up to booting the operating system and then to actually running the Rocket pods, you have this testable chain of information about what exactly is running on the system, so you can sort of cryptographically verify it. Matthew, I'm not going to talk about this in any detail because I don't know, I'm not a security expert. Matthew is, and he's going to be talking about it tomorrow, so I'd encourage you to check out his talk if you're interested in more detail. Something else that's pretty new in Rocket was this API service. So it was a very intentional design decision that we didn't have an API from the beginning because, again, we want Rocket to be very well-scoped. Didn't want to have some... we didn't want to mandate that you need to run a daemon to use Rocket. You still don't need to. But the API service is like a sort of optional extension that allows you to optimize for certain use cases, primarily integrating with something like Kubernetes. Because then rather than forking and executing the Rocket process every time you want to get some information, you can talk to this service that understands the Rocket internals and can provide that information. And then another really key aspect here is that we set up the permissions so that it can run as an unprivileged user, so it doesn't need to be running as root to provide this information. It only provides read-only information. You can't use it to start pods or containers or anything like that. But this is what the kubelet uses to get information from Rocket in certain areas. So why Rocket? Why should you use it? Why do we think it's cool? We have a focus on security and composability, and we are pretty dedicated to implementing open standards. Okay, so finally getting to Rocket and Kubernetes. Why are we integrating, or what are the ways that we're integrating these things? There's 3 key ways. The first is rktnetes, which I'll probably spend most of the time talking about. But then there's a couple of other ways that I'll touch on as well, which is using Rocket itself to run Kubernetes, which gets us to an interesting sort of inception situation, and then how Rocket networking works and how that integrates with Kubernetes. So how do we integrate Rocket with Kubernetes? What does that mean? Well, fundamentally, I'm sure Kubernetes, on every node in the cluster, it runs something called a kubelet, which is responsible for actually running pods on the system. But the kubelet doesn't understand anything itself about necessarily like how to run a container. For all that, it sort of delegates. So by default, it delegates to Docker, and it uses Docker to run containers. But now, the idea is that we can make that pluggable. So Kubernetes defines an interface. The kubelet defines an interface in the code, which is just called the runtime interface, and that defines these sort of operations like sync pod, get pod, kill pod, that then container runtimes can implement to actually to become like a swappable container runtime. In theory, it's pretty straightforward to just like implement this interface, and then suddenly, great, you have a new container runtime that Kubernetes supports. But in practice, there's a lot of assumptions in the code, in different parts of the code, in this, and also elsewhere in Kubelet that do assume Docker, and so there's a bit of work to be done teasing that out. We've spent a lot of time refactoring a lot of that code to make it more agnostic before we can actually get to implementing Rocket support. But basically, this is a pretty high-level overview of what it looks like for Kubelet for a standard kind of Kubernetes node where Kubelet's talking to Docker to run containers. So the Kubelet just talks to Docker over its standard API, and then Docker is responsible for actually starting up the individual containers. There's a couple of problems with this, and again, this is kind of like motivation for why we want to integrate Rocket with Kubernetes. The first key problem is that Docker doesn't understand the concept of pods. Docker just has the concept of individual containers. And this means that the kubelet itself needs to track this mapping between what its idea of a pod is, so the different applications and containers that constitute a pod, and what those containers are that are actually on the system. And then the kubelet also needs to do these sort of weird tricks, like it needs to maintain a what it calls an infra container, which is basically just a sleeping Docker container, that holds the namespaces that constitute the pods. Because a pod, by definition, shares namespaces between the apps. So this is kind of hacky. It's not ideal at all. The other key problem here is that the Docker daemon is essentially a single point of failure for all the pods running on the node, because if the Docker daemon dies here, then all the containers are necessarily going to need to be restarted. And then finally, as I sort of touched on earlier, slightly related problem is that Docker doesn't integrate that cleanly with systemd. So currently that's not necessarily a problem in some default. I think like the default GK instance isn't running systemd yet, but sort of in the future Linux world where almost all operating systems are going to be running systemd. It's pretty unclean integration between that and Docker containers. So in contrast, Rocket, we hope, sort of improves on all these areas. The first is that Rocket understands pods natively, and this is what I talked about earlier, where we define appc pods as pretty much synonymous with Kubernetes pods, and appc pods are what Rocket implements. So Rocket understands things at the pod level, so that when you have an operation like, for example, sync pod, rather than the kubelet needing to sort of glue together these different individual containers and sort of maintain all that state itself, it can just talk directly to Rocket and say, hey, create this pod or kill that pod. It doesn't need to maintain all that state because Rocket understands the pod abstraction. We also have first-class integration with systemd. So what that means is, for example, Rocket pods are registered with systemd's machine D, and so they're recognized as containers by systemd. And it works very, since it uses, by default we use systemd internally as well, it sort of maps very cleanly with the systemd C group hierarchy and things like that. And then since we have this this self-contained process model where each Rocket process is what starts up the pod and applications underneath it, there's no single point of failure because there's no central daemon that's responsible for looking after them. And then finally we get these nice other benefits that Rocket provides is that, for example, since we support Docker images in Rocket, and as well as appc images, then you can still use all your Docker images with this particular kubelet, and Rocket will support them just fine. So, kind of contrasting to the Docker image, like what this actually looks like when we're integrating Rocket with a kubelet. So now, instead of the kubelet talking to the Docker daemon, what we actually do by default is that we talk to systemd. So this means that Rocket Netes today does require systemd to be on the host. Again, we don't think that's going to be a problem because many operating systems have already moved and most are planning to move soon. And in this case, the kubelet talks to systemd in order to start Rocket containers. So it actually submits a unit file to systemd saying, hey, start up this Rocket command, and then systemd is responsible for tracking those pods. On the other side, I mentioned the API service, which is sort of an optimization. So the kubelet can talk to the API service to get information, to extract information about pods and images that are on the system, and it can talk to that out of band with managing the lifecycle of the pods. The nice part about this, architecture is now that almost any of these components can fail without affecting any of the others. So, for example, if the API service dies, then it's no big deal. Your applications continue to run. It just means the kubelet might briefly have some unavailability of some information while the API service restarts. If the kubelet restarts, it doesn't affect the life cycle of the pods at all. If an individual pod dies, since now we're looking at each of these as actually a pod rather than an individual container. If a pod dies, it doesn't affect any other pods on the system. Systemd will just sort of clean up after it, and then the kubelet will, recognize that and start it again. Excuse me. And then finally, so the only sort of point of failure here is systemd itself. But if systemd is hosted on your system, then your whole system's hosted anyway. So we're not introducing any components for failure here. That's sort of a natural dependency of running a modern operating system. Another, like an alternative model that we've sort of discussed, which would, again, we sort of believe that systemd is going to be the future, but this would make sense if if people do want to run Kubernetes on non-systemd nodes, is that the kubelet itself, thanks to the Rocket process model, where again it's just running directly under the process, the kubelet itself could actually take over direct responsibility for managing the Rocket pods. So the kubelet could actually spin up, the processes, the Rocket processes, and apply all the constraints it wants to directly to those pods. And then it can manage them just fine. Obviously, the problem there then is that the kubelet becomes a single point of failure. But if it restarts, then it's going to take down the pods with it. You're kind of back to the Docker problem. So that's how we're integrating Rocket and Kubernetes today. And the current state of it, it's really close to being complete. I think as of yesterday, we're at about 80% of end-to-end tests passing, which is kind of our benchmark for right now for like what we consider it to be complete. That number's fluctuating a bit since they're adding tests and removing tests and so on. The only main, I think, thing that's sort of still in flight, aside from just like polishing some edges, is working on CAdvisor integration. So CAdvisor is used to expose resource information, and it sort of runs within the kubelet to expose resource information on running containers. And it doesn't. Again, there's quite a few assumptions in there about it being Docker containers. So we're in the process of adding support so that it can properly recognize Rocket pods. How are we doing for time? So the other way that we integrate Rocket with Kubernetes is actually using Rocket itself to run Kubernetes. So Kubernetes is largely self-hosting, so the control plane and stuff can run on top of the kubelet. But fundamentally, you need to bootstrap a kubelet somewhere on the host. And since on CoreOS, everything we do, every application we do runs in a container, we need to do this in a container. But the kubelet has some special responsibilities since it needs to do things like mutate mounts and stuff like that. And if you're running in a classical container where you're in an isolated environment, you can't do those things. So we introduced this feature 1 or 2 releases ago called Rocket Fly, which doesn't execute pods. So it's not an implementation of the AppC or Kubernetes pod model, but it allows you to still take all the advantage of all the nice features of like image management and verifying signatures and fetching applications off the internet, and then running them in sort of an unconstrained environment instead. So, before we looked at when we execute a pod with Rocket, it sort of creates this separate stage 1 thing where the pod encapsulates all the isolated mount namespace, PID namespace, network namespace, and stuff like that. In contrast with Fly, we just basically execute the application directly on the host. And in this case, the kubelet, that means it has access to the host mount namespace and stuff like that. So the kubelet can do all of the operations that it needs to do. So that's how we run. The kubelet on CoreOS itself. The other aspect where we integrate and starting to integrate even more is with networking. So going over this pretty quickly, with Rocket, we have this modular networking system that we originally started within Rocket, but then we split it out into a separate project, CNI. And the key ideas here are that it's based around plugins, so that there's an abstraction so that you can implement different plugins to provide different networking backends without the container runtime having to understand them. And also that you're going to assign 1 or more IPs at the pod level, not at the individual app level. So again, CNI is just like the abstraction between whatever your container runtime is and then different kinds of backends. So there is a Flannel plugin. I should have maybe put that as an example. For example, different backends to talk to something like Flannel, to allocate an IP to a pod. Pretty quickly, CNI is really, really simple. Honestly, it's just basically a command line interface and a configuration file that supports commands like add this container. And in this context, a container just means a network namespace on Linux. So in the context of a pod has a single network namespace. Add it to a network or remove it from a network. And then that's all the container runtime needs to do. And then the plugin itself is responsible for talking to Flannel, for example, talking to whatever. Maybe you have some backend IPAM, custom IPAM system or something like that. Talking to something like Calico or Weaveworks. And setting up the network namespace. This is a really simple example of what a CNI configuration looks like. Very, very basic one that's just going to allocate like a local IP address, doing a point-to-point. So it sets up an IP address inside the container and connects it to the host. And there's an example down the bottom of how you'd actually reference that on Rocket, just basically pointing it to my net, and then that's going to look at the configuration file and pass that through to CNI. So again, Rocket doesn't do any networking stuff itself. We just basically call out to CNI for that entirely. So at just before we spin off systemd nspawn to set up the container itself, we actually call out to CNI before that to do all this stuff. So Kubernetes networking, from the beginning, it was had pretty similar kind of design principles, that it was going to be plugin based. There's an IP is always assigned at the pod level. But they sort of had a plugin system, but it never really left kind of an alpha stage. But recently they've decided that it's going to become the default plugin system for Kubernetes, which is really nice, because then all the work that we've done that everyone's done with CNI and different plugins they've written will work natively with CNI. With Kubernetes. So in the last few months, we've really seen adoption and use of CNI kind of skyrocket, which is interesting because it's still not quite at 1.0. It's sort of a V0.x at the moment. We have been using it in Rocket for a long time, very successfully. It handles all the networking in Rocket, and we've recently seen these integrations with different projects like Calico and Weaveworks. Whoops, I guess I'll jump ahead a little bit. So I've got about 10 minutes, so I'll talk a bit about some other stuff that's coming. So the first is RocketNetes 1.0. As I said, we're nearly there, but not quite. But we're really targeting by end of quarter, and we're hoping we can get it to have it sort of fully supported with the next release of Kubernetes 1.3. And a key aspect to that for us is having fully automated end-to-end testing on CoreOS, so that every time a change goes up to Kubernetes, that we're actually running that again with the Rocket backend on CoreOS. And then kind of looking forward for next sort of steps with RocketNetes. We want to, I mentioned the LKVM backend. We're really interested in exploring that having it as like the default backend for Kubernetes, which means that then you have your Kubernetes cluster is using hardware virtualization to isolate pods, which is pretty cool. And then the next big thing, going back to sort of the discussion around container images and standards and stuff like that, is extending the Kubernetes API to support different kinds of images. So at the moment, the only image type that Kubernetes API supports is Docker images, which is fine because Rocket supports Docker images natively, but there are certain issues with that, particularly around sort of namespacing and discovery, and we would like to extend that to support different image types. The reason I have this little star here about sort of ACI versus OCI is because, as I mentioned, the standards, it's a little bit unclear where all the standards stuff is going to play out. We're really hopeful at the moment that the OCI, which is the Open Container Initiative, there's a new proposal to actually standardize an image format in there. There's been a lot of contention over the last 6 months about whether that's within the remit or not, but now there is a proposal that's been accepted by the OCI technical committee, technical operating board, to standardize an image format, and we're hopeful that that will sort of take the best of like the Docker v2 image format and some of the things that we tried to introduce in AppC, and create a sort of next-gen image format that we can all agree on. And as soon as that's the case, then we're really going to push for that to be in the Kubernetes API, and we're definitely going to support it in Rocket. And fortunately, that's going to be sort of minimal code changes. It's really just about coming up with something we agree on. And then finally, or not finally, but the other thing we want to focus on really soon is integrating this sort of TPM support that I talked about, extending it up to the Kubernetes level. So, before I talked about how we use the TPM to trust up into the point of like actually running pods, and then we also want to use it to ensure that only trusted machines can join a Kubernetes cluster. And again, Matthew's going to be talking about this in much more detail tomorrow. We also have a white paper on the website if you want to read more about it. And then CNI, the next thing that's coming up is that we need CNI to reach 1.0. We need it to reach something where we can call it stable and agree that, hey, this is we're happy with this model right now. We're happy with the configuration format. There's a couple of big changes, or not, maybe big changes that we have in mind before we reach 1.0. For example, like IPv6 support. We think that shouldn't be too much difficult. We just need too much trouble, but it would be really nice to have that land before 1.0. And then also some changes around sort of the state model. So right now it's the responsibility of individual plugins to maintain any state they need, for example, if they're allocating IP addresses. But we've been talking about pushing that responsibility back to the runtime, which means then like something like Kubernetes can persist that state. But as like I said, this is very much kind of work in progress. So if anyone's interested in networking, I'd really encourage you to kind of get involved. We're definitely looking for to bring people on to help kind of maintain CNI and thrash out what 1.0 is going to be. So come find us at the booth. The lead maintainer of CNI is here at the conference. And then in sort of the 1.3 timeframe, we're actually looking, or the Kubernetes team is looking to push all the networking code that the kubelet currently does into CNI plugins, so that CNI is basically the only way that that kubelet can do any of this networking stuff. The nice part is we're able to rip out a ton of code from Kubernetes for that. Another thing that we're looking to do at sort of CoreOS is working on the different ways to upgrade the kubelet to make this a bit of a nicer experience. Previously we experimented having the kubelet in the OS, which meant when you do an upgrade, it's sort of in lockstep with the OS image itself. But we had some issues with mixed cluster versions, unfortunately, where there wasn't actually the sort of strict compatibility we'd expected between I think the control plane and the API. And there's, if you want to see more details about what exactly we hit, there's a GitHub issue there. So our solution to that is something we're exploring, which is like API-driven upgrades, where you have a little agent on your host that runs the kubelet using Rocket Fly, as I talked about earlier, and then that's actually just using the Kubernetes API, like annotations that we have, like against an individual kubelet to say, which version of the kubelet it should be running, and then you can do like a nice phased rollout or whatever of kubelets across your cluster. Again, I put a GitHub issue there if you want to read more details about that. And then another aspect is the Graceful kubelet shutdown. So when I talked quite a bit earlier about when a system needs a reboot and then it can gracefully migrate the apps to another server, that's not actually the case today. What happens today is the server will go down, then Kubernetes will realize that the apps need to be migrated, so it'll do so. But it'll be nice to be able to do that proactively rather than reactively. So in CoreOS, we have a component called Locksmith, which is the thing that's responsible for saying, hey, I've got an update now, it's time to reboot. So what we're going to do is try and wire this up to the kubelet so that when Locksmith says, hey, I've got an update, it can tell the kubelet, hey, I'm going to reboot soon. I'm going to reboot in 5 minutes or something. And then Kubernetes can sort of mark that machine as needing what we call maybe draining or maintenance. And then Kubernetes can migrate the apps sort of gracefully before shutting down the machine. Again, we have sort of an issue tracking the work on our side in CoreOS, and then there's an upstream issue in Kubernetes about the work that needs to be done there. So TLDR, get out there and use Rocket, use Kubernetes. Really encourage you to get involved as well. As I said, we're super close to having rktnetes reach kind of 1.0. I'm really hoping expecting that's going to happen for 1.3. And get involved and help kind of define what's happening with application containers and Kubernetes in the future. Also, just to quickly pimp our conference, we're having CoreOS Fest in Berlin in May, where we're going to be talking about all these kinds of things related to Kubernetes and runtimes and distributed systems. And I have about 2.5 minutes if anyone would like to ask any questions. Yes.
Yeah, I have a mic. I'll pass it over.
How do you handle the Rocket containers? Sure. Because in Docker it's the JSON file thing, and is it integrated in the API?
So the question was, how do we handle, I guess there wasn't any other question, how do we handle logging within Rocket containers? So we actually just defer to systemd for the logging. So Rocket integrates with, as I said, we integrate quite closely with systemd. So you can look at the systemd journal to get the logs, both at the pod level and at an individual app level. And so the Rocket API service that I talked about actually talks to systemd journal. So the API service exposes the logs basically by just talking directly to systemd journal. So that abstracts it so that kubelet doesn't need to understand the systemd journal. But if you want, you can just go on and look at the systemd journal however you normally would, and you'll see app logs for pods and at the app level if you want.
Like kube-control logs would still work?
Yeah.
Kube-control logs would still work was the question.
Yeah,
awesome. Did I see?
So, great talk, by the way.
Thanks.
Thank you very much. I was wondering, I mean, we are all Kubernetes guys, and we love the pod concept, but what is your take on why does it have to be in the Rocket runtime? It feels like it's another abstraction layer and that it should be like stage -0, I don't know. But it's like, why is the container itself not in stage itself, and why is not the pod concept at the Kubernetes level? Why does it have to be in the runtime?
Well, I think, the first way would be if we talk about look at how you have to end up implementing something like a pod in the kubelet, like with the Docker containers. You end up having to sort of create these different disparate containers, one of which hosts the namespaces, and then you have to attach the other containers with it. It's quite an awkward model. part of the other answer is that we think when you have these different applications running in a pod, you need something to manage their life cycle, and we think that should be managed by like basically a proper PID1, something that knows how to track processes and cleanly handle them, handle their life cycle and stuff like that. So we think that should be the responsibility of the runtime. So you don't need to introduce some other component. Otherwise, for example, you would need, and that's largely around like things like when you start up a new process namespace, right? PID1 within the process namespace has kind of special responsibilities. So we think, for us, the cleanest way to solve that is to make the PID1 in the process namespace to be a proper service manager that can like look after the child processes. I don't know if that answers your question at all.
I don't know if it's to implementation detail, but it.
You mentioned some of the inspiration for Rocket was to make innovation in the container runtime space. Do you feel like some of that has like gone back into Docker itself, or any other container runtime implementations I don't even know of?
I think definitely around the standardization stuff. I think we can see that's had a really tangible impact in terms of writing down what the Docker image format is. Like there was no real drive to do that until after we tried to kind of kickstart all this. On the technical side, certainly around maybe some stuff around overlayFS and SE Linux, for example. Since we started, for example, Docker supports a bunch of different storage backends. We just went kind of straight to overlayFS, and so we've been doing a lot of work there, like upstream, that ends up filtering back into Docker, in their overlay implementation, and getting overlay to work together with SE Linux. I'm sure we'll see some similar stuff with the TPM, eventually.
Any questions of that side of the room at all? Go on in.
Hi, great talk, by the way. In terms of defining kernel capabilities in Rocket, what's the level of granularity provided by the Rocket whole ecosystem here?
Capabilities?
Yeah.
Sure. So that's actually defined in like the AppC spec. So when you're defining an image, you can define basically just provide a set of capabilities that you want to allow or revoke, and then we pass that through to the apps. So
thanks.
All Linux capabilities.
So I see everyone moving outside for lunch actually now. So it's probably best to go out, otherwise we're going to get mugged and not actually get our lunch. But Jonathan, you're around all day by the CoreOS booth.
Yeah,
You'll be happy
feel free
to
to
take
come by. I'll be
questions.
around today and tomorrow at the CoreOS booth.
Thank you once